We are pleased to have James McCurry as our presenter. James McCurry is a senior applications chemist specializing in analytical chemistry measurements for the chemical and refining industries. He is a member of the American Chemical Society and the American Society of Testing and Materials. James holds a BS in biochemistry from the University of Scranton and an MS and PhD in chemistry from Lehigh University. All right, it gives me great pleasure to turn today's event over to James McCurry. Jim, please go ahead. I think you might be on mute, Jim.
Okay, there we go. Okay, thanks, Madison, and I'd like to extend a welcome to all of our attendees and express my appreciation in taking time out of your day to attend the webinar, and hopefully we can provide some good information for you in terms of Intuvo's capability for doing Ultrafast GC, and for those of you who are interested in total petroleum hydrocarbon or TPH analysis, how this can improve your laboratory productivity when running those methods. So I'm going to now share my presentation so that we can all see that. Okay, so as the title suggests, this is looking at ultrafast GC, and in particular applying these ultrafast chromatography techniques to total petroleum hydrocarbon or TPH analysis, and in specific on the Intuvo GC system. And we see a little photograph here of Intuvo. It's a unique looking instrument as well as a unique performing instrument. So let's take a look at what I'm talking about when I say total petroleum hydrocarbon analysis. Those of you who are familiar with this environmental application, you'll know that there are many different flavors of TPH. In particular, I'm going to discuss an ISO method, which is ISO 16703, and how we applied this method to the Ultrafast GC techniques running on Intuvo. So first, let's take a look at the scope of the method. And I'll put my laser pointer up here. So for the scope of a method, what it seeks to measure are C10 to C40 hydrocarbon contamination that's in the environment. So this could be a number of different types of samples. Specifically, where this hydrocarbon contamination comes from is from the accumulation of what we call in the energy and chemical industry middle distillates and lubricating oils. Middle distillates being things like diesel fuel, jet fuel, home heating oil, and so forth. These get into the environment by spills, leakage from delivery mechanisms such as pipelines and trucks, and also just from, say, spills coming from ships. Now, the contamination can exist in different types of environmental samples, water, soil, and sediment. The ISO 16703 method addresses specifically soil and sediments. There are other international and U.S. methods that do address water matrices for this analysis. The concentration range covered by the scope is between 100 milligrams per kilogram and 10,000 milligrams per kilogram, and that's in the sample itself, so in the soil or sediment specific to ISO 16703. What's unique about this method is we don't actually measure individual hydrocarbons, but we measure the entire hydrocarbon load that can be found in these environmental samples. Therefore, speciation or separation of individual compounds is not really necessary. We're really just getting them through the GC basically as a broad elution profile and then measuring that broad elution profile without really any regard to individual compounds. Although that's not entirely true, we do need to see two of the marker peaks, and we'll see that in later slides, the C10 and C40, which denotes where the elution profile for quantification exists. So for this method, for the sample analysis, first, there's a relatively rigorous and complex sample preparation that is multi-step. And this is used to extract the hydrocarbons from the matrix. But when you do the extraction, a lot of other things from the environmental samples will come along. And we want to eliminate those. So there are several steps that seek to clean up as much of the environmental matrix as possible and leave behind only the hydrocarbon contamination that we're trying to measure. Once the sample is prepared, they're then analyzed with gas chromatography by running the extracts through a GC column with detection by a flame ionization detector, or FID. Now, if we look at this method, some of you who are maybe familiar with simulated distillation or SIMDIS methods, this method looks very similar to that. And in fact, some of the ASTM SIMDIS methods actually seek to measure the same range of hydrocarbons in actual fuel samples as we are measuring here in the fuel once it's contaminated in the environment. So there's a lot of overlap and similarities between methods used in the industry for energy production and then also in environmental laboratories. Typically what we'll be using is a high temperature GC, so we want to go from roughly ambient conditions, a little bit above ambient, 40 degrees centigrade, and then program the GC column up to 350 degrees. And we'll be doing this with a fast temperature program ramp, as we'll see in later slides. And as I mentioned previously, the only two peaks that we really need to identify are the C10 and C40. These are retention time markers that are actually spiked into the sample. And these denote the start of the elution profile of the hydrocarbons and the end of the elution profile of the hydrocarbons that are included in the scope of ISO 16703. A key to the performance of this method is reducing boiling point discrimination, particularly for the high level and low level boiling contaminants or boiling components that are in the extracted hydrocarbons. If we don't eliminate discrimination, this will cause a failure to achieve accurate quantification. By discrimination, what I'm talking about here is inlet discrimination. So with improper injection technique, you may actually lose some of the low or high boiler components. They're not transferred effectively from the inlet to the column, and thus we will skew the quantification of the sample. So there are a number of tests that we have to meet to demonstrate reduction of boiling point discrimination, and I'll show how we meet those. Okay, so TPH using ultrafast gas chromatography, and I've abbreviated that by UFGC, is shown here. So the fact that we are not doing compound speciation or trying to separate all the compounds is an ideal situation for trying to apply a method to ultrafast GC because we don't really have to worry about chromatographic resolution. So with ultrafast GC, the definition of that is typically its analysis times in the 1 to 3 minute range. And the way that we achieve this is with rapid column heating. So typically we'll ramp the oven temperature for the GC column at 100 degrees per minute or higher over the entire temperature program range. So for this particular method, it'll be from 40 to 350 degrees. Another technique for ultrafast GC is employing short, narrow columns, typically in the 3 to 5 meter range, whereas most of us who use GC columns will be using them somewhere between, say, 15 and 30 or 60 meters. This is quite a short column. And shorter columns, of course, produce faster analysis time, but it does that at the expense of chromatographic resolution. But as I said, for this method, we're not seeking chromatographic resolution. We just need to get that profile or that envelope of hydrocarbons through the column as quickly as possible. And then finally, the third technique that defines ultrafast GC are using higher carrier flow rates. Typically, will go greater than 5 mils a minute. For most narrow bore columns, we're usually running column flow rates from about a half a mil a minute to maybe 2 or 3 mils a minute. So we go quite a bit faster when using ultrafast GC techniques. Some of the challenges that are presented to us when trying to do ultrafast GC is, first of all, retention time precision. And what we're trying to do here is make sure that the retention times don't drift. And when we're ramping the oven very quickly and using high constant flow rates, there's an interaction between the column ramping temperature and the control of the pressure and thus flow through the column that has to be consistent from run to run. Otherwise, you won't get good retention time precision. If you don't have good retention time precision, then trying to integrate the envelope of the compounds that are eluting and identify the marker peaks can become very difficult. So with ultrafast GC, you need a good interaction between very precise column temperature control and very precise flow control while you're rapidly heating that column. Another challenge for ultrafast GC, particularly for this method, is column lifetime. Since we're going up to 350 degrees, that rapid heating and that higher temperature that's being applied to the column can cause the column to degrade. There's several different modes of degradation that can happen. First, if you're using columns that have a direct heating element wound with them, one of the examples of this is there are low thermal mass columns. Rapid column heating and then cooling to high temperatures can affect some of the heating elements there and cause failure. One of the primary modes of failure is the polyimide coating on the column. These columns are glass, but they have a polymer coating that makes them flexible so that when they're bent, the glass doesn't break. This polyimide coating, though, is not totally inert to the atmosphere, and it can break down. So when we're rapidly heating the high temperatures, the polyimide coating will eventually oxidize over time, and as it oxidizes, it will expose the glass, and that can cause column breakage. Then finally, the last mode of column failure with ultrafast GC is the stationary phase. Typically, we're going to be using thinner film stationary phases, again, to reduce the retention time or the hold time for the later eluting peaks. And with thinner stationary phases, they will degrade faster when we're rapidly heating to high temperature. So all these things need to be taken into account when looking for a GC system to do these high temperature ultrafast techniques. Okay, so let's take a look at the Intuvo and some of the features of Intuvo that are specifically designed to do ultrafast GC. So with Intuvo, we have a new column heating technology. We don't have a column in an air bath oven that we're typically used to. We have a unique approach to column heating, and this is a direct column heating pad, and I'll show a photograph of that in a moment, that applies the heat directly to the column. It doesn't heat the air around the column, it heats the column directly. What this allows us to do is to rapidly heat the column, and in this case we can go up to 250 degrees per minute over the entire temperature programming range of the oven, and that's 40 to 450 degrees. Because we're not having a complex wrapping of a heating element and temperature sensing around the column, it's more of a direct heating of the instrument to the column. There are fewer elements to fail, so this will ensure better lifetime of the columns as we run more and more samples. The next feature of Intuvo that allows ultrafast GC techniques is the next generation EPC, or electronic pneumatic control. This is a new generation. I think it's our 6th generation of column EPC, and this works in conjunction with the rapid heating of the column to deliver the precise constant carrier flows that we need to do the fast GC as we're heating the column to very high temperatures. What this will do is the working of these two elements, the column heater and the EPC, to give us precise flow and precise heating. That will assure that the retention times are consistent, as well as give us more stable detector response. So let's take a look at Intuvo. Now, Intuvo has a lot of new and novel GC features to it. I'm not really going to discuss all of those today. We just have some of the benefits are shown here. First of all, it's easier to use. Installing columns and maintenance is much easier. It's faster. This is the main point that I'm going to be focusing for our Ultrafast GC is the speed. It's also, as you can see, it's a smaller GC, so you can pack more of them into a laboratory space than with a conventional air bath oven GC. Then also, it's smarter. It has a lot of built-in intelligence, and with the introduction last year of Agilent's 8890 and 8860 GC, we've improved the smart capabilities of that platform and have taken those new features in terms of smart GC and put them back into Intuvo. So brought Intuvo up to the current level of GC. And then also we say it's greener. It uses less energy because we're not heating a big air bath oven. We're only heating the specific elements that allow us to do gas chromatography. So let's take a look at the inside of Intuvo. So when you open the door, there's actually two doors. This is the main door here. We've taken off here the column oven door. And we're going to just focus here on the column oven, our direct heating element. You can see that the column, if we look over here at the column, it's in a different format than we're used to seeing. It's not wound on a cage. It's actually wound in a planar format. Because it's now all the coil wrappings of the column are in one plane, we can press that against this heating element. And behind here, it looks like a mirror, but that's actually our direct heating element. And then when we close the door of this, a pad will go over the column, push it into the heating element, and eliminate all the airspace there so that the heat is directly applied to the column, not to the air around it. When the run is over, the heating pad moves away, and there's a separate fan down here at the bottom that will blow ambient air across the column and the heating pad or the heating element to cool it down very rapidly. So not only does it heat up fast, but it also cools faster than a typical air bath oven. So this and the new generation EPCs is what's going to allow us to do these ultra-fast GC techniques. Here again, we can see a closer view of the heating element. So you can see this looks like a mirror behind here, but it is actually a planar, thin heating element that the column is pressed against. And then the column is connected up here to the flow path to our inlet and detector. Okay, so let's look at the specific way we're going to apply Agilent's Intuvo Ultrafast capabilities to making the TPH method according to ISO 16703 faster. So we're not going to be using the instrument conditions specifically outlined in the ISO methodology, and that's because it is geared towards an air bath oven, and we're going to be using Ultrafast GC. So we're going to be using a shorter, thinner film column than what's in the ISO method. We're also going to be using higher flows and also faster temperature program ramps in order to get this analysis done faster. The other parts of the method in terms of the hardware will be the same. We're still going to be injecting the sample onto the column with a splitless inlet, and we're going to be detecting using a standard flame ionization detector. Now, in order to test our method, I'm going to actually run real samples. And the samples that I obtained come from this organization here. I'm not going to butcher the pronunciation of it because I don't speak German, but it is shortened into the acronym BAM. So we bought certified reference samples from BAM. These are real world samples. So this is real river sediment and real soil that has been known to be contaminated with the TPH range oils or fuels. These river and soil samples were then divided up and sent to a number of different laboratories. Those laboratories use the ISO 16703 method to measure the TPH. And so they have what is called a consensus value. So all that data is pooled together so we have an idea of what the contamination level is in each of the samples and what the precision obtained by all those laboratories was for running these samples. The way we're going to do this, we're going to take these samples and we're going to prepare them multiple times using the sample prep protocol outlined in the ISO method. So the steps are shown here. So we're doing ultrasonic liquid solid extraction with an acetone and heptane solvent. Then we're going to decant off the extraction liquid, and we're going to centrifuge that to remove the fine particles. Then we're going to do a liquid-liquid extraction cleanup to remove the acetone. This will be using water with a separatory funnel. And then finally, we're going to be using a solid phase extraction or SPE final cleanup. What this cleanup does is removes all of the naturally occurring organic material that's in these soil and river sediment samples that comes through the extraction process. And so this will eliminate a lot of the background contamination and then just leave behind the hydrocarbons that we're seeking to measure from these samples. So in this case, we're following exactly the ISO 16703 protocol for sample prep. For the GC part of it, using the Intuvo GC, we're going to be doing a 0.5 microliter injection, splitless inlet in the splitless mode. This is important. The focus liner that we're using is one of the key elements to try to get the best performance in terms of inlet discrimination. So this will really help to vaporize the wide boiling range of the sample very quickly and then transfer that in a representative fashion from the inlet onto the column. And the inlet temperature is going to be 350 degrees. Now, Intuvo has two other heated elements here that we need to be aware of. There's the guard chip. The guard chip is a device that's in between the inlet and the column that can be used to trap any heavy sample matrix from getting onto the column. But because we've done this really very exacting and rigorous sample prep, we're not really going to be doing or transferring too much nonpolar or high boiling matrix to the column. But we do have to be aware that the guard chip is there as a protective device for keeping the column operating correctly. So this has a separate temperature control, and so we're going to put this in what's called track oven mode. So it will start at about 50 degrees above our starting temperature for the column oven, and then it will track the column oven, and when column oven reaches its maximum temperature, the guard chip will come to its temperature as well. There's also what's called the bus temperature. This is just the flow path that the column takes between the guard chip and the column, and then from the end of the column to the detector. And again, we're going to leave this at 350 degrees, which is similar to the splitless inlet. The column we're using is a high temperature column. It's a DB1 HT. As I said, we're going to be using a shorter column, so 5 meters, 0.32 millimeter ID, with a thin film, 0.1 millimeter film thickness. And for doing high boiling components, thinner film columns like a 0.1 millimeter allows those high boiling components to elute out of the column faster. As I said, we're really trying to improve the speed here. And towards that, we're using our helium carrier gas at 10 mils a minute constant flow. And here's our oven temperature program. So we're starting at 40 degrees centigrade, holding that for about a half a minute. This will allow transfer of the heptane solvent and then all the components from the inlet and give us a little bit of solvent focusing. And then we're going to rapidly ramp up at 250 degrees a minute, the maximum ramp rate for Intuvo, to 350 degrees a minute to very quickly get that hydrocarbon profile through the column and into the detector. And then we'll hold for half a minute. And finally, the FID temperature is held at 350. So let's take a look at some data now. So the first thing we did when we were testing this method with Intuvo is we wanted to make sure that the column performance was good over a long period of time. Because we're doing really ultrafast GC, this will allow laboratories to run a lot more samples in a given workday. And so we want to make sure that with that large number of samples that are being run, the conditions or the performance of the system isn't changing in a short period of time with the large number of samples that are run. So this is a performance test mix for the Ultrafast GC TPH method. Here we see our C10 to C40 peaks with some other peaks in between here. You can see now the runtime that C40 is eluting in less than 2 minutes. It looks like the C10 elutes just under 1 minute. And what we're looking at here is agreement between the first injection and injection number 1500. And you can see that the retention times really haven't shifted very much. They've gotten a little bit shorter, but not significantly shorter. Also, you can see the peak shape is maintained. So although we're losing some stationary phase, because the phase will bleed off over time, we're not really losing so much that it's affecting the peak shape. We're just getting a little bit shorter retention time. And for various systems that we've tested, we've gone up to 3,000 injections before the column needed to be changed. So let's look at the inlet discrimination test. This is an important test. You have to meet the 16703 requirements before you can really run any samples. So you can purchase a performance test mix for discrimination. This contains hydrocarbons in a heptane solvent from C10 to C40, and we're going every 2 column or carbon numbers, so C10, C12, etc., all the way up to C40. Now, according to the method, you look at your C20 peak, and that becomes your reference. So that has a defined recovery of 1. And then you look at the C40 peak, and you ratio the area between the C40 and the C20, and that ratio has to be greater than 0.8. And you can see here for this method, or for this run, we're getting 0.93. So this is essentially telling us that we're not losing any of the higher boiling or lower boiling components during the injection period, because you can see here the C10 recovery is 0.98. We pretty much stay almost 1 all the way up to C36, C38, and then C40 is 0.93, which is well within the range specified by the method. Also want to take a look at the calibration performance. So the method requires you to run the middle standard, so peak standard number 3. You run it 3 times, and then you look at the total area of the elution profile of the hydrocarbons. So here's our C10 peak and our C40 peak. We set our integrator to sum all the area at the end of the elution of the C10 and the beginning of the elution of the C40. And we just look at that total area under this profile. And we do that 3 times. We get the average and then the standard deviation and the relative standard deviation. And according to the method, the RSD has to be less than 5% RSD. You can see here we're less than 2% RSD. So this is telling us that we've met the discrimination test, we're meeting the calibration test. And then finally, you have to look at the calibration curve itself, and you need to have at least a 0.99 correlation coefficient. And here we have a 6-level calibration and our correlation coefficient is essentially almost 4 nines. So we're meeting that test as well. Okay, so let's look at a real sample that's being run here. So as I said, I took the two samples and extracted them multiple times, and then we'll do multiple injections of those samples. But let's take a look at one of them. So this is the soil sample. So this is our BAM U021. This is a soil sample that's been certified to have a mineral oil contamination in it. So this is the actual run. So here's our heptane solvent front. We can easily separate our C10 marker from the solvent front, and then our final marker, our that should be C40, sorry, that's a typo. So we integrate between the C10 and the C40, and we also want to make sure that our retention times are the same. So let's take a look at another extract that I did of the same material and overlay that. Now you can see that this chromatogram is in blue, and when I do the overlay, I'll color that chromatogram in red. And as we all know, if we mix red and blue, we get purple. So let's take a look at how good the overlap is between our two sample preps run on Intuvo. So we'll move that on here, and you can see that we get near perfect overlay of the two samples, two separately prepared samples run on two different runs. You can see now the chromatogram looks purple, so it gives us an idea that there's a near perfect overlay both in retention time and in peak intensity. So we're getting exceptionally good precision on our retention times, and also we're not getting any inlet discrimination or removal of the higher boiling components. Let's take a look at the same sample. This is 10 different sample preps that were run, and we're looking now overall the retention time stability. And you can see here I focus on the C10 peak, which is our first marker, and the C40 peak, which is our second marker. So I zoomed in on those, and you can see the range here of the retention times. So for the C10, it's 0.751 to 0.754. So that's extremely precise retention time precision. And again, for the higher boiling components, it's even better. We're only 0.001 minutes difference between the high and the lows of these 10 overlaps. So we get RSDs for retention time precision that are much less than 1 for the C10 and much less than 0.1 for the C40. Okay, so these are two of the samples that we ran, so just showing example chromatograms. So in the upper one, we've seen this before. This is the mineral oil sample in the soil that's extracted from the soil, and this is the mineral oil contamination in the river sediment. River sediment is quite a bit more challenging because, as you can imagine, there's more of a natural organic load in there. So when you extract this and clean it up, it looks like a much dirtier sample. And that's very important to use the solid phase extraction cleanup at the end to eliminate all of that. And then finally, let's take a look at the quantitative results. So as I said, I prepared each one of the samples twice, ran them 5 times each for a total of 10 runs. So this is the soil sample, this is the river sediment sample. And so we can see what Intuvo is going to deliver is method accuracy. So look at the mean here for our 2 samples that I prepared. So I have 3,500 milligrams per kilogram on sample prep 1 and 3,484 for sample prep 2 of the soils sample. And the certified value, the consensus value that BAM has published with the method is 3,560 plus or minus 260. So you can see that we have near perfect agreement with Intuvo running the Ultrafast method compared to laboratories running the standard ISO 16703 method, which is about a 30 or 35 minute runtime. Again, if we look at excuse me, the river sediment samples, these are a little more challenging, of course, because they have a higher matrix load, a lot more cleanup that has to be done. You can see again our 2 sample preps and our 5 runs of each one of those. And we have a measured value of 8709 milligrams per kilogram and 8647. And again, you can see that is near perfect agreement with the certified value of 8270 plus or minus 550. So we're getting very good accuracy. We're really agreeing with those laboratories that are running the standard slower ISO method for TPH. We can also look at the instrument precision. So if we just look at the RSDs for these results, you see that the RSDs for all of them are less than 1%. And so this shows very high instrument precision. But we also want to look at the method precision. So the method precision includes not only the instrumental analysis, but also the sample prep. So the way the instrument or the method precision is defined is reproducibility, so small r. And the way that you do this is you measure the difference between 2 identical analyses of the same sample, and that difference has to be less than what's published in the method. So for the soil sample, the difference between 2 sequential analyses has to be less than 136 milligrams per kilogram. If you see here, our difference on average is about 60 milligrams per kilogram. So this again is showing very high method precision. For the soil sample, the difference between 2 identical analyses of the same sample should be less than 337 milligrams per kilogram, and we're measuring 126. So not only are we getting good instrument precision, but the method precision is also extremely high. So in summary, we're able to develop an ultrafast GC method that completes a total petroleum hydrocarbon sample run in 3 minutes as opposed to 30 or 35 minutes. And we do that by using shorter columns and take advantage of the Intuvo fast oven programming with the 6th generation EPC to deliver precise hydrogen carrier constant flow rates. The Intuvo GC has its direct column heating and the 6th generation EPC, so that's what makes this possible. And because of this, there's no need to do any post-run lineup manipulation of the data. Some instrument vendors will do that. They're not getting good retention time precision, so they'll use chemometric techniques to then adjust that retention time. There's no need to do that. We naturally and organically get extremely good retention time precision with our direct column heating and our pneumatics column flow control. So this ultrafast GC method, it meets all of the ISO performance benchmarks for selectivity, resolution, discrimination, and calibration. So we've shown that the quantitative results for the certified reference materials show extremely good agreement with other laboratories running the slower version of the ISO method. And then we also have extremely good repeatability compared to what we'll typically find with the published ISO 16703 method. So for the value proposition for what Intuvo can bring to your laboratory using Ultrafast GC is lower cost of ownership and return on investment. You can improve your laboratory throughput up to a factor of 10 or even higher. We get greater column lifetime. The guard chip will replace a retention gap and protect the column from matrix contamination. And then also, it's a simpler column format, and there's less degradation, less complexity to the column when doing this rapid heating over and over again to high temperatures. So the column should last longer using an Ultrafast GC method with Intuvo. Ease of use. Because of the high throughput of this, laboratories are typically used to changing the columns fairly often. The columns will degrade over time, mostly related to the stationary phase degradation. And with Intuvo, I didn't really go into it, but some of our other webinar series will. It's easier and faster to change the columns, especially compared to something like LTM or low thermal mass columns. There's no complex unions or connections to make, and the guard chip is easy to change, and that eliminates retention gap trimming. So for further information for this particular application, we do have an application note that's published. This is the document number. So if you go to Agilent's website, type this document number into the search field, you'll get a PDF of the application note. So that concludes today's webinar on showing how Intuvo can be a financial and a technological improvement to your laboratory, particularly using its capability for Ultrafast GC. And I'd like to turn it back over to our audience to see if there's any questions.
All righty, wonderful. Thank you so much, Jim, for that wonderful presentation. So before we go to our Q&A session, I just want to open up our short polling survey concerning today's presentation. While this poll is optional, we do appreciate you taking the time to answer each question, as it helps us with modifications for our future Intuvo webinars. That poll is now open on the lower right side of your console. We thank you for completing the survey. All right, and on to our Q&A session concerning today's presentation. You may ask questions at any time by placing them in the question box located on your WebEx platform. If you would like to ask a question over the phone line, please click the raise hand icon located on the bottom right of your WebEx. I will receive this notification and unmute your line, where you will then be able to ask your question. Alrighty, so our first question. So we have noticed with the fast, rapid heating and cooling of our Intuvo GCs, the temperature sensors for the guard chip and detector seem to fault after a couple of months of use. Is there any development on improving the sensors to handle the higher temperatures?
Yeah, I know that with the first generation of Intuvo, particularly if we're running high temperatures, there have been some decoupling of the heater element from the guard chip heater. Those have been redesigned, and there was a service note that was put out, and so those can be upgraded. And the other thing you want to make sure is that you don't heat the guard chip more than necessary. In this case, I was using, for this analysis, the oven track mode, so it stayed at its high temperature for a relatively short period of time. And that worked perfectly well for this analysis. Some customers think that, or will suspect that hotter is better, and that's not always necessarily the case. So you want to make sure that you don't heat it first to too high of a temperature for too long of a period of time. Also, when the instrument is idle, you probably want to have a idle mode or an idle method that has that at a lower temperature. And leaving it at, say, 150 degrees is perfectly fine. That will avoid buildup of any contamination, say from your carrier gas or from any septum bleed that may work its way through.
Wonderful, thank you. Next question. Why did you choose helium as the carrier gas? Why not H2 or N2, considering helium storages and most TPH methods are ran by environmental labs, which are all about cost-saving measures? Right.
So that's when we did this application in 2016, there wasn't as the supply and the cost of helium had come down from previous problems that had happened several years before that. And in the subsequent time, the shortage and expense of helium has gotten worse again. So that's something that we definitely want to go back and take a look at. Now, based on other experience with converting methods from helium to hydrogen, this would be actually a fairly easy conversion. what we could do is just leave the hold up time or the linear velocity the same as the helium. And in that way, we won't get any difference in retention time. So it'll all be roughly the same just with the hydrogen carrier gas. There may be actually a way to do a little bit of speed improvement again with hydrogen. Nitrogen, didn't really think about that. As you go to higher temperatures with nitrogen, it's a more viscous gas, and it requires higher pressures to push that through a narrow column. Our EPCs for capillary GC, although they can use nitrogen, they really can't deliver the high pressures that are always necessary for higher flow rates at high temperature. And so I didn't really consider nitrogen for that. But hydrogen, you make a good point. Hydrogen is something that should definitely be tried, especially these days. And I think it would be a fairly fast and easy way to do that. And that's something that we should take a look at going forward.
Perfect. Thank you. Our next question, can the Intuvo be used to run Texas method 1005? It uses carbon ranges of C6 to C12, greater than C12 to C28, and greater than C28 to C35.
Yeah, Intuvo could certainly be used to do that, but not with this method. As you saw, we're using, in this method, we're extracting our samples with heptane. And in the Texas method, which is used by a number of different states, we need, as you pointed out, we need to get down to C6. So that heptane wouldn't be an appropriate solvent. Typically, something like methylene chloride or pentane is used. But trying to apply that, looking at those lower carbon numbers using this ultrafast method, particularly this particular ultrafast method, we looked at it and it definitely does not work. There's not enough ability to separate the solvent from the lower boiling components with this particular column. Now, one could use a longer, slightly thicker film column, and I know some of our colleagues in Europe have done that, and that seems to work pretty well. So you don't get the less than 3-minute run times. They're a little longer, and I know they've used, say, a 15-meter column with say a 0.25 micron film thickness, and have gotten good separation and good retention time stability with the C6 to C12 carbon range. And so that would have to be a separate method. For the higher boiling portions of the Texas method, it probably could, this technique, or what I described here today, could probably be used. There may be some adjustment in the ramp rate that would have to be done to get good separation. But this is really geared towards the middle distillates, the C10 to C40 range. A separate method would have to be developed for other ranges.
Okay, perfect. Next question, how does the Intuvo liner used in this method compare with the multimode inlet for conventional GC methods?
Well, when we did this, the multimode inlet is a temperature programmable inlet, and that's not really necessary for this method. So that is a thinner bodied splitless type method or type inlet that also has a cooling coil on it. So with Intuvo, you can run air through it to rapidly cool it. I have run this method at the request of some of our European customers using the multimode inlet, and it worked just fine. So there really wasn't any significant difference between using that and the splitless. Although I didn't really take advantage of the temperature programmability of the multimode inlet. So really, it's more expensive inlet, so I don't know what it would get you other than more flexibility. So if you wanted to use this Intuvo for other things where temperature programming the inlet was required, then that would give you more flexibility, and you could run this method on that, just leaving the inlet temperature at 350 degrees like we did with the splitless.
Perfect. Let's see. Another question, does the Intuvo have an optional H2 sensor to shut down the GC if a leak is greater than 1 or 2%?
No, it does not, but you have to remember the Intuvo does not have an air bath oven like our conventional GCs. So there isn't a big open void inside where hydrogen can collect. And so you really would never be able to build up the hydrogen to the level where it would reach the lower explosive limit. In addition to that, Intuvo has, I think, 4 or 5 internal fans that are constantly moving air through the Intuvo. And so there isn't really any way that hydrogen could be built up. Now, given that the Intuvo does have in the EPC the safety features that all of our other inlet EPCs have. So there's a limiting frit built into the EPC, so it caps off the amount of carrier gas, and if you're using hydrogen, the amount of carrier gas that we get through the EPC into the inlet. So that caps that off. In addition to that, there are pressure and flow sensors. So if there's a breakage anywhere in the flow path, that would be sensed by the EPC, and the instrument would go through a shutdown mode. So everything would be cooled off, the EPC would be turned off, and it would stop the flow of the carrier gas, the hydrogen, into the inlet. So that safety feature is inherent into all of our EPCs. But there really is no place to put a hydrogen sensor, and there's really no, as I said, air voids inside the instrument where hydrogen could possibly build up.
Perfect. Okay, thank you, Jim.
Mm-hmm.
All right, so I don't see any other questions in my chat or Q&A box. At this point, I'll go ahead and take over. Jim, there might have been some questions that may have been delivered to your chat or Q&A box, so if you want to check, I'm going to go over a couple of points before we start closing out. Please note that this is an ongoing series of our Intuvo webinars. They do run monthly, so you can see our next 4 months listed in the slide currently displayed. Jim does come back in September. And then this is going to be the URL where I post all of the recordings. I'll post today's recording here, as well as emailing it to everyone. So usually within 24 to 48 hours, I will send out the recording. I'll send out links to register for next events. So be on the lookout for that in your inbox in the next day or two. I have also included Jim's email address here in case you would like to ask him questions directly or have any follow-up or feedback of the sorts for any questions he answered today. But Jim, is there anything else that you would like to go over, any questions that may have gotten delivered to you that we had not discussed yet?
No, but really appreciate all of our participants, and especially the really good questions that were asked. I think this shows that there is a real interest in Intuvo in general and in running faster TPH analyses specifically. So I do plan to look at some of the water methods for TPH running on Intuvo as soon as our COVID-19 restrictions are lifted and I can get back to the laboratory. So we should see some more information about TPH type analyses on this platform.
Wonderful. Thank you, Jim. All right, everyone. So it appears we've reached the conclusion of our event. So please join me in thanking Jim McCurry for his wonderful presentation. I will leave the session open for a few minutes to receive any feedback or additional questions, but we are now going to close the audio line. Thank you all once again for attending, and on behalf of Agilent Technologies, we wish you all a great day.